All right, we are going to pick up right where we left off. In this case, we are given a couple of functions that are in a slightly different format. So rather than being given the equation, we are instead given this as a table or as a couple of tables. And our goal is to try and see, can we figure out what kind of transformation is taking place here? Is it going to be horizontal or vertical, and then what is kind of the direction of that transformation? So taking a look at A, is this going to be representing a horizontal translation, horizontal shift, or a vertical shift? This is going to be horizontal. Why do we know that it's going to be horizontal here, Oliver? Yeah, notice that the y values are all staying the same, but the x values are changing. And how would you describe the change of the x values here? Okay, yeah, so equation here, we're going to get to that. I totally agree with you that this is going to be that g of x is equal to f of x minus 1. And what direction, what shift does this x minus 1 tell us? Which way are we moving? Yeah, we're moving to the right. Our x values are all increasing by 1. Now, again, this is a little bit odd because it feels like, we increase by 1. Why wouldn't we add 1 to the x values? But if we think about like plugging in a particular value of x here, notice, for instance, that g of 3 is the same thing as f of 2. And that g of, let's plug in 0, is the same thing as f of negative 1. So our values for our function g, each of those x values has increased by 1, but they are always 1 more than the values of f. And so if we're trying to adjust f or adjust g down to f, we would need to subtract 1 off of the input. Again, we are shifting to the right, the x values that we see here shifting all to the right. And so we would say, yes, to capture that shift, we do the opposite. That is x minus 1. Very, very good. Okay, for h, what is changing for our function h here? X's or y's? Okay, so our y's are going to be changing. So we've got a vertical shift. And then how would we describe this change? What's happened to my y's? They've gone up 1. Each one has increased by 1. Vertical shift, this is going to be exactly what you'd expect. We take our original output, and what do I do to it? We just add 1 more to it. So B, a lot of what we expect, kind of vertical shifts work like that, right? If we want to move 3 up, we take our output and we add 3 to it. Go figure, that's going to move us 3 up. Horizontal shifts, again, a little bit trickier. We think, what do we have to do to undo what we are seeing? Well, in this case, to undo this minus 1 on the inside of my function, I would have to increase each of these inputs by 1. And we see that for our function of g, where each of the inputs is increased by 1. Yeah. So when x in this case is 0, so notice that that negative 2 is in relation to this minus 3. It is 1 more than that negative 3. So we're basing it off the top one. Yeah, so we're always trying to compare it. How does it compare to this function f? So notice that g, each of the inputs is the same, but each of the outputs is the same, but the inputs are all kind of reordered. They're shifted. Whereas with b, each of the inputs is the same, but each of the outputs is 1 more. So instead of negative 2, we have negative 1. Instead of negative 1, we have 0. Instead of negative 3, negative 2, and so on. So all of our stuff is pushed up by 1. Yeah. Good question. Other questions here? Feeling pretty good with our shifts? I'll take your silence as a resounding yes. Then let us move along to our kind of next to transformations here. Again, thinking in this case, we've got one vertical, one horizontal. What is the vertical telling us? What did the vertical tell us that we were changing last time? Changing the y values. Okay, so we're going to be reflecting the y values, whatever that means. And then horizontal before meant that we were changing the x values. So in this case, a horizontal reflection will be doing something to the inputs. What that something is, what does a reflection do? Vertical to our outputs, horizontal to our inputs. This is going to switch all of our positives and negatives. So, for instance, a vertical reflection takes our standard parent function f of x, and what does it do to it? Well, it turns it into the negative version of f of x. All of the outputs that are positive become negative, and also all of the outputs that were negative become positive. It completely flips upside down this function. Looking at our graph here, if our parent function is again f squared, we could think of the reflection f prime of x, that is negative x squared, as really just taking this function, and instead of having positive outputs, I would have negative outputs. So flipping it entirely upside down. Oftentimes, you will see this referred to as a reflection about the x-axis. So we could call it a vertical reflection, or we could say that our function has been reflected about the x-axis. Which I always find a little bit confusing, or I feel like can be a little bit confusing. We're changing the y values. It's a vertical reflection. So what do you mean we're doing something with respect to the x-axis? Think of reflecting about a line as telling you what's not going to change. So for instance, if we're reflecting about the x-axis, the x values don't change. Those all stay the same, but what does change? Well, the y values are going to kind of rotate around. And in this case, I mean rotate in the sense of like, picture this graph kind of coming like forward out of the page and like flipping upside down. So starting kind of facing up like this, and then kind of swiveling forward until it's upside down. So not a rotation like in the 360-degree sense, more of just like a kind of falling forward through the page. All right. If our vertical reflection is taking the outputs and making them the negative versions or making them the opposite versions, what is our horizontal reflection going to do to f of x? Yeah, it's going to make the x on the inside here the opposite. We've seen something like this before. Where have we seen f of negative x? When have we talked about that? Yeah, those are like our even and odd functions, right? Where our odd functions, when we plugged in negative x, turned into negative f of x, and our even functions just kind of stayed the same. What does this tell us? Well, this tells us that our even functions are kind of what I would describe as like immune to horizontal reflection, which is to say, if I were to switch all of the positive and negative x values, our function would not change. Picture it here with our function of x squared. What kind of function is this? X squared is going to be an even function. And if we were to flip it around the y-axis, kind of rotating it in its place, notice that it's not going to change. It doesn't move at all. That is because this function is even. Okay, so maybe as a parent function, picking an even function to display what a horizontal reflection would do was a bad call. Let's come up with a different function then. We'll say that g of x is like the square root of x. Interesting things to note about the square root of x. The outputs are always going to be positive, right? A square root of a number is always going to be that positive square root of a number. And then what has to be true about my inputs? They have to be also positive numbers. My function is going to look kind of like this. Okay, so let's apply the horizontal reflection to this function. Instead of the square root of x, let's think about what is the square root of, we'll call this g prime of x. This is going to be the square root of negative x. Okay, square root of negative x. We are only allowed to take the square root of positive numbers. When is the square root of negative x? When is negative x going to be positive? When x is what? Yes, when x is 0. Are there any other values? Yeah, sorry. If I plug positive 1 into x there, I'll get the square root of negative 1, which is an issue. When x is either 0 or negative. If I plug a negative value into x here, I would get like, if I plug negative 4 in, negative 4, which is positive 4. And so what does this transformation do? Well, rather than plugging in the positive versions of numbers like positive 4, positive 16, so on, we would plug in the negative counterparts. Do my y values change at all? Am I changing the outputs that I'm getting? No, I'm just changing the fact that they appear now on the other side of my graph, the other side of the y-axis. It is now only for those negative values of x that we see this occur. Okay. I want to spend just a quick second. I want to pause and look at this notation here, the square root of negative x. Because I think a lot of people would look at this and say, well, but we can't take the square root of a negative number. So what do you mean we're taking the square root of negative x and it's not just like a nothing? Like, how can we do that? Remember that x is not positive or negative, right? X is a variable. X can be at some points positive and it can be at some points negative. Taking x and multiplying it by -1 does not guarantee that we are looking at a negative number. It looks like x is negative here. It does, right? Negative x looks like x would be negative, but it's only negative for positive values of x. X is negative, just kind of like what we said, exactly like what Bryce said. When x is negative here, negative x is a positive number, which is weird. On the quiz, we kind of ran into a little bit of that. I ended up giving full credit for this. But for instance, if people said that the absolute value of negative x was equal to x, I gave credit for this because I knew what you meant. But the more precise way to say this is that the absolute value of negative x is the same as the absolute value of x. Because what if x was negative 7? Well, then plugging negative 7 in over here, I would get positive 7. But over here, I would get negative 7. And positive 7, negative 7, not the same. But what we know about those two is that when we take the absolute value of both of them, they will in fact be the same. So negative x, not necessarily a negative number. Depends on that value of x. A little bit tricky. Again, I gave full credit for if you wrote that the absolute value of negative x was x, because ultimately I understood what you were trying to say, but do kind of keep in mind that it's not like it's clearing out the negative. It's that because negative x is not necessarily a negative number, which is weird. Certainly a little weird. All right, questions here about our reflections? So reflection just means like you're multiplying by -1, exactly like before. Horizontal reflection means you're multiplying by -1 to the input. Vertical reflection, multiplying by -1 to the output. And you can think of this as flipping around a certain axis, and that's fine. You could think of this as like, how is it going to rotate? That's fine. But algebraically, multiplying by -1. All right. Quick little aside. If a vertical reflection is a reflection about the y-axis, what is a horizontal reflection going to be? Or sorry, about the x-axis. Yeah, this is going to be a reflection about the y-axis. Freudian slip there. Fantastic. All right. Last two that we are going to cover. I'm not going to cover these in an extreme amount of detail. We will talk more specifically about these particular kinds of functions when we are doing trigonometry, or these particular transformations when we are doing trigonometry. They have very specific names for when we are doing them with trig. I'm not really going to focus too much on them. Beyond that, there will be a couple of instances where we need to find those, and we'll deal with those as they come up. But at the very least for now, I really want you to have a strong kind of conceptual understanding of what these do rather than a particular like computational understanding of what these are going to do. All right, so we'll say, yeah, we'll work with this. Okay, so the final two transformations that we're going to look at, I've kind of lumped them together. Compressions and stretches are really the same thing. They do the same thing. So I'm lumping them together as one transformation. Again, vertical means that we are affecting the y's, we're affecting the outputs. A vertical compression or stretch is going to be taking our output. So from f of x, we are going to be multiplying by some kind of constant number a. So taking that output f of x, multiplying it by a. What is our horizontal stretch or compression going to do? Not negative a. That would be both a compression or stretch and a reflection. What are we going to do with the horizontal? So dividing is a good idea. Division falls actually under the distinction between a compression and a stretch. So we'll look at an example where we divide here in a little bit, like what happens if we divide by 2 instead of, say, multiply by 2. We'll look at that behavior here momentarily, but that's a good idea, but not quite it. Where are we going to be affecting if we're affecting horizontal? Yeah, we're multiplying the x value here by a. Okay, this has some very, very distinctive effects that oftentimes you just don't even get to see. Oftentimes, these kinds of compressions do about the same thing. Not always. And in fact, when we are working with trig functions, what each of these do is very, very specific. It's very, very particular. But a lot of the times it's going to be the same. For instance, for the parent function that we're looking at here, it's going to be the same. I'm going to do my best to kind of enumerate on what are the kind of subtleties of what we're doing here. But oftentimes it's going to be the same effect, like the same kind of effect. For the most part. Okay, so let's say we want to look at the transformation that is f prime of x. We'll say that this is 2 times x squared. Is this going to be vertical or horizontal? Are we multiplying the x first and then applying the squared, or are we doing x squared first and then multiplying it by 2? Are we doing the x directly? No, PEMDAS says first we do the squared. So first we deal with what on earth is x squared, and then after the fact, after we've resolved that whole what is our function doing, then we multiply by 2. Okay, some options for you guys. I claim that this function is going to look like one of 2 functions compared to our parent function here. All right, our function in red. Is it going to be the brighter blue one, or is it going to be the pink one, and why? Yeah, I think that that's a really, really good idea. And I think that this is what my other classes answered as well. I think that this is a very visual kind of way to look at this, is that 2 should make it bigger, and so it would be pink. I want to veer away, for this specific reason, I want to veer away from thinking of that 2 as making us larger for this specific reason. All right, so really good idea. My other class answered the exact same thing. The 2 is not going to make us larger. It's going to make us faster. So rather than thinking, 2 means I get big, think 2 means I climb quickly. I reach larger y values, larger outputs for smaller values of x. Okay. So this 2 here tells me I grow fast. Okay, let's address Keenan's question about division. If I were to divide by 2, or we could think of that as like multiplying by 1/2, which of these graphs would I look like? In that case, I would end up looking like the pink one because I am going more slowly. So dividing by 2 makes me grow more slowly, and so I end up being a little bit closer to the ground, a little bit lower, right? But I like the idea of multiplying makes me big. It's just the thing that gets big is the speed at which we hit large y values. So notice over here, these y values are larger than the y values from the original function. Whereas over here, they are a little bit smaller. Fantastic. Yes, Sadie. Right now, this is vertical compressions or shifts. Or not shifts, sorry, vertical compressions or stretches. So this is like we are taking the y value and we are doubling it. It is getting taller. Or we are cutting it in half. It is getting shorter. And ultimately, that's either going to make our function fast or it's going to make our function slow. Yes. Them apart. Yeah. Okay. Fantastic. Let's take a look at a horizontal one. You might not be satisfied with the answer here, which in part is that it can be difficult to impossible to tell the difference between the two. So rather than 2 times x squared, let's look at 2x squared. So notice the distinction here. I am doubling x and then squaring it. Okay, so let's think about what this is going to look like. And Sadie, the reason why this is a little bit unfortunate is I can ask the same question. Is this going to look like my blue? Or is this going to look like my pink? And again, what we are going to see is it's going to look like the blue again. And that's a little bit weird. Because oftentimes, again, this is just kind of an annoying thing, not always, but oftentimes, our vertical and horizontal compressions, like our vertical compression can be written as a horizontal compression, or our horizontal compression can be written as vertical compression. Not always, definitely not always, but certainly in the case of like an x squared. Okay, so let's maybe try and clean this up a little bit. What's different then about a vertical compression and horizontal? Vertical compression is drawing us up. We are growing more quickly because our y values are being doubled. We are being stretched in this direction. Horizontal compressions mean that we are going twice as quickly through the x values. If I plug in 2 for x, it's like plugging in 4 up here. If I plug in 7 for x, it's like plugging 14 up here. Right? We get to large x values very, very quickly. What does that do to my function? It's like an accordion. I'm like squeezing in the space. I'm compressing, I'm shrinking the amount of space that it takes in order for me to reach these larger x values. Yes, no. And then
So in what case does it look like the pink one?
Okay, yeah, fantastic. So when would it look like the pink would be if I were to be multiplying by a number less than 1. So kind of like what we were talking about, like Keenan asked, what happens when we divide? The answer is dividing means we go more slowly through the x values. Plugging in a 3, picture this as like a 1 over 2, dividing by 2. Plugging in a 4 is like plugging in a 2 up here. Plugging in an 8 is like plugging in a 4 up here. It's a lot more slow. It takes a lot longer to get through the x values. It's like taking our accordion and stretching it out the other way. So we have one that's like compressing our space. That's why it's compression. Squeezing in the x values into a much tighter, more narrow window. The other one is stretching that window out a lot longer.
So for horizontal, you'd rather be stretched out, and vertically, you'd rather be squeezed in?
I mean, so think of large numbers as making, well, and again, it's like, it's hard because like this particular function kind of combines them, and they are a little bit different for other functions. Let's look at one where it would be a little bit different. This is one that's going to come up later a lot, and this is actually where we would kind of need this idea. These are good questions, and I don't want to kind of lead you astray with this. So let's say we're going to look at the function that is sine of x. And this is getting way ahead of ourselves, but it does a really, really good job of kind of showing the difference between a horizontal compression and a vertical compression. I'm just going to graph a little bit of sine of x. We'll focus on this particular function a lot more later, but sine of x is called a wave function because it kind of caps out at a certain point, and then it also repeats on and on and on forever. So a wave that would maybe look like this. Okay. And maybe we'll say, for the purpose of it, maybe this value of x is 0, and I don't know, let's just throw a random thing that we'll explain later. This is 2 pi. Don't worry about it. What would multiplying the outside of my sine function by 2 do? Well, it's going to double my output of my sine function. So that is going to make it so that I am twice as tall at every single value of x. Okay. So doubling my sine function made me twice as tall. What if I had cut my sine function in half? It would have been half as tall. You get little lumps there. How is that going to be different than something like sine of 2x, where I multiply on the inside? Well, now, how long does it take for me to go from 0 to 2 pi? X only needs to be equal to pi. It's half of what it would take for me to get all the way through this kind of up and down bit. If it takes half as long, if I move twice as fast, it's going to take half as long. This wave is going to be compressed like an accordion into half the amount of space. It's going to look like, let me again try to be a little bit precise here. Whoop. It's going to look a little bit something like this. I can clean this bit up a little bit more. Or notice, have the y values actually changed here? No, the heights are still the same. They're just like pressed together more closely. And oftentimes, that's just the same thing for our functions. Like with our x squared, our x's being pressed together more closely makes our function hit large y values more quickly. It's just kind of the way that function works. Yes?
Is that a horizontal compression?
Yeah, so this would be a vertical stretch, and this would be a horizontal compression. And isn't that lovely that they go? But that's kind of why I tried to kind of explain it as one transformation. The vertical transformation is drawing us, again, kind of like an accordion, either larger or pushing us smaller. And the horizontal is doing the exact same thing, but in the other direction.
Oh, so they're opposites in the way a vertical takes a 2 and makes it a stretch.
Yeah,
Horizontal
exactly.
makes it compression.
Yeah, fantastic. That's very true. So vertical is like stretching us like taffy, we get taller. Horizontal is like squeezing us in like an accordion, we get smaller. And those are for values of A that are large, that are greater than 1. Yeah, very good. And oftentimes have overlapping results, exactly like what we see with x squared, but note that it is not the same thing, and this is a really good kind of demo of them being different. But here they are the same, or at least can be kind of thought of the same. Yeah. So. Yeah. So what I have drawn here is like a single wave of this function. You could picture mirror images of this extending infinitely in both directions, but you get a repeat image every so often. If we're traveling twice as quickly, it takes half the amount of time to get a single repeat image. So this is telling us that we travel twice as quickly through the x's, so it takes up half the amount of space before we see one copy of the wave. which is called a period, and the period of this would be pi instead of 2 pi, and we'll get into all those specifics in a second. Don't worry about this function in particular. You're not going to see it again for like 2 more units. And then it'll be back in unit 4. Full power. I care a lot less about the stretches and compressions. I just want that kind of idea of if I multiply the outside by 2, I'm like stretching it vertically to be the case. I'm making it faster. If I multiply the inside by 2, I'm like compressing. An interesting way, so I think Keenan's way of thinking of like them being opposites is really good. Whatever we do to the inside of our function is kind of like the opposite of what happens when we do it to the outside, right? So in this case, multiplying by 2 squeezes things really, really tight. You have to plug in smaller values of x to see the corresponding values of y. Right. Cut your values of x in half to see those particular. And so again, it kind of follows similar to the ships. Yeah, very good. Very good questions. Very excellent. All right. Any other questions with any of our transformations before we move on? All right, we'll say bye to sine of x for now. He'll be back. Enjoy the absence while you can.